Well, the copper bulb has been a Minecraft snapshot feature for a few weeks now. The one tick delay was fun while it lasted, but I've been focused on the more direct purpose of the block, which is the compact and movable 1-bit data storage. There have been plenty of Redstone computers before, but the thumbnails will never lie about how big and complex such a system needs to be before it is useful. I admittedly can't say that this is a simple and perfect solution either, but I think this is comparatively more reasonable, and it's a good demonstration on how big of an improvement the copper bulb is for general purpose computation. Data storage and movement has always been one of, if not the most complex part of Redstone computers. I sort of wonder how much Mojang intended to target that specific issue. This particular Redstone computer is designed based on a specific esoteric programming language, which, for the sake of YouTube, I will refer to as BF. BF has only 8 different operations, and converting them to Redstone turned out to work pretty well. Turned out to be pretty straightforward. It does result in very long, hard-to-read programs, but it's the kind of programming language that, with enough time and effort, it can theoretically complete any calculation that another computer can do. That makes it Turing complete, though, again, it is very long and complicated to do such a thing, so it's often also referred to as a Turing tar pit. It's still very well designed, though, and it can be used to demonstrate a few important concepts in computer science. Now let's go through how I've accomplished this in Minecraft. Some people may know from recent Redstone reveals of the snapshot that copper bulbs can be used as a simple binary counter with just comparators between them, if you consider them inverted. However, that doesn't work for this circumstance because they can't be moved by pistons in that state. So, here is the first section of my Redstone computer, my binary increment and decrement, my binary math system. This one does the same thing. I don't have to invert the bulbs anymore. It's just a binary counter with a binary subtractor right here. It uses a trick called 2's complement. Since I'm only going down by 1, since I'm only decrementing by 1 anytime, all I need to do is invert the copper bulbs, add 1, and invert them again. So this simple circuit is all I need to do for math in BF. Expanding outwards, BF operates on a infinitely long tape of memory. So here we have the same increment and decrement system as before. But with some additions. Right here, we can see that if we add 1 and 2, but if we press this button, then we will move that value of 2 to another slot, and we can use the second value, the second 4-bit value in this case, to store another number. Pressing this button will then shift our registers downwards and switch back to where we stored the 2, which we can then continue to subtract from. The addition of these redstone blocks and target blocks is used for both a reset circuit If we go here and switch over to this value, this button will let us reset the value, as well as letting us take a second output and a second input line. But this circuit right here will do all of the math we want it to for a number. This is 4 bits. The full version I converted to 8 bits, but this will store 35 different values. And, well, technically, the target goal is infinity. 35 is quite plenty for anything I might use it for. From there, that circuit was then plugged into the larger computer and expanded to 8 bits. The different operations were then color-coded, red for plus and minus math, dark green for the shift up and down, and brown for input and output. The 8 levers on the bottom technically work as input, but this is not the ideal setup. But you could theoretically attach the 8 brown input lines to any kind of input system and take an input from anything that you wish to use to calculate. Above that, we have another output system, which I have attached into this very long 8-bit wide piston feed tape. These copper bulbs then allow for very easy data output, as the current value in the memory stores will be copied over to this line of copper bulbs and then moved across this effective screen. That allows me to store a very specific amount of characters across a very long screen. It then cycles back. Takes a while, but hopefully you're not outputting things into this system fast enough for it to be a problem. I will mention that the clock for this Redstone computer is not very constant, and I've allowed each operation to take a different amount of time to simplify and speed things up. Now I'll quickly go over how we store the programs themselves. This 4-block wide piston feed tape is bidirectional. This does make it a lot harder to make it fast. It does need to be very fast to keep up with the program. This feed tape does almost dictate some of the timings of the system. Many of the operations are slower than the feed tape, but addition especially is slowed down by the feed tape itself. Moving in both directions and being as long as it is. Ideally, this would be even longer. Right now, this stores 91 4-bit values. Each value is an instruction, and they are read from this line. Programs in BF are often much, much longer. The standard Hello World example that people use on the internet is about 600 characters long. Or I might be mixing that up. But it's much more than 100 characters, and there's plenty of example programs that are 600 characters long. More complex example programs tend to go into many thousands. So, designing programs to work in 91 operations has been a noted challenge. By use of the clone command, I've been able to copy the programs here, and some of the programs I've just split into 2 sections, which is annoying but effective. Anyway, each operation is 4 bits. The bit on the far left is start and end program. Theoretically, if you could fit more than one program onto the tape, you can. And these bits would designate where to start and stop and divide between programs. The other 3 bits handle the different operations. I've organized things into pairs so that the rightmost bit, using the rightmost bit. So, increment and decrement are the first two operations. Shifting upwards is, shifting up and down is 3 and 4. Or 2 and 3, technically. Input and output. And finally, start loop and end loop, which are much more complicated operations I will describe in a minute. These different operations are then decoded by this system here into their 8 different slots. And that is then represented by this circuit, which loops into the lime green clock system. Finally, the blue section is the start bracket and end bracket. For BF looping mechanics, I recommend reading the resources in the description, as it is a little more complicated to go over in a short time, and as only really useful information to those who are very interested in the computation. To continue the demonstration, I can come over here and clone one of my existing programs using these white wool blocks as convenient markers. Once this is done, I will use this button to clear the memory via command, as well as clear the current output. Running this program will unfortunately take a very long time, but I have been making good use of the tick sprint command in developing and testing this. However, before that, I can run through a good portion of the program to demonstrate what it looks like. As you can see, we are adding many numbers to a starting counter and cycling through a few different variables to do so. Once we get to this closing bracket, the first blue circuit will activate and will loop backwards through the program. This counter will keep track of how many open and closed brackets the program runs over until we reach the matching bracket right here. The program will then resume as normal and continue with the same math. By setting up a variable before the loop, this loop should run 6 times in order to operate correctly. This program has multiple nested loops and will take a while to reach the target numbers, so let us tick sprint about an hour to watch how it processes. With better timing, I probably could have watched the final creeper face being output, but here you can see the program was successful. During the program's run, you may have noticed one nested set of loops. A loop that ran 6 times, containing a smaller loop that ran only 4 times, each loop doing a number of operations to a number of different variables. After that set of loops was completed, a second nested loop did a little bit more math. And finally, the creeper face was output onto the screen. Planning out that program did take quite a lot of effort. Not as much effort as the large Hello World program you saw earlier. However, this has been a good demonstration, and this is a good point for this system. I'll have a world download in the description, and this is a good demonstration on how I think on the many improvements that copper bulbs will provide to computation technology. It's been a very interesting project working on this. And if someone wants to improve this system, there are many places where such things could be done. Thank you.